Hello, students. This is the astronomy chapter on atmospheres, which I think is interesting. I hope it's all right for y'all. I don't know how much y'all go into in elementary science classes. Um, Atmospheres are interesting. I'm sure you've seen the water cycle and things like that. So I'm not going to spend a huge amount of time on that. We're going to spend time on other stuff. So, definitions: atmospheres are layers of gas that surround the planet. Earth is about 10 kilometers thick. What we mean by that is the majority of, the largest part of the atmosphere is within the first 10 kilometers. And it's mostly nitrogen and oxygen. It's about 4 parts nitrogen, 1 part oxygen. And then there's some other stuff. Atmospheres have pressure because, gas particles have mass and they have weight. And in general, the pressure is higher near the surface and low near the edge of space. And so, we give what Earth's pressure is at sea level. There's not a clear upper boundary, is that you can find small amounts of stuff very far from the surface, hundreds of kilometers away. But in general, as a legal thing, space is about 100 kilometers up. Here's a picture of the space shuttle in orbit about 300 kilometers up. And there are effects that can only occur when there's particles there, when there's atmosphere present. In this case, aurora. And so atmospheres are going to determine whether liquid can exist on the surface. It's going to scatter and absorb light. It's going to allow for weather and climate to form, and it's going to create wind. It'll interact with the solar wind, and so you'll have a magnetosphere around the planet. And they can act as insulators. They can hold heat, what's called the greenhouse effect. And so we should talk about the greenhouse effect. And this is purely just a physics thing. Light comes in one wavelength and it's absorbed by the ground or by objects. And then that energy is re-radiated. Right? All objects with a temperature radiate. And the lower the temperature, the longer the wavelength. Right? That's the thing we discussed in chapter 5. So light comes in at all different wavelengths, and it heats the surface of the Earth. The surface of the Earth is fixed at one temperature, so it's mostly centered around one infrared wavelength. And that infrared wavelength is easily absorbed by the atmosphere. So it kind of randomly is absorbed and re-emitted by the atmosphere until it leaks out. And so the temperature is determined by how much energy is received from the sun and how much can be radiated out as thermal radiation. And the amount that you receive is based on the distance from the sun. And there's also an effect of the rotation rate. Is if there's a clear day side and a night side, and they swap places, then you have kind of even heating. If they don't swap places fast enough, then one side gets extra hot and the other side gets cold. So also important is how reflective the surface is. And the reflectivity of a planet is called the albedo. And that represents the fraction of light incoming that is reflected. The shinier the planet is, the lower the temperature you'd expect. And the darker the planet is, the more absorptive the planet is, the higher the temperature. So we can calculate what the temperature would look like if there was no atmosphere, if there was no greenhouse effect, if all the energy coming in leaked back out effectively. And so we can look at the reflectivity and the distance from the sun, which tells us how much energy is going to be absorbed. And so what we see is, in general, as you go outwards, there's going to be a cooling effect. Right? And it wouldn't be very, very warm without an atmosphere. All right, we see a difference between, Mercury effectively doesn't have much of an atmosphere, so its no greenhouse temperature is kind of the average of what the day and the night temperature. And the moon is roughly the same. But Venus is warmer because of its super thick atmosphere. The Earth is warmer because of its atmosphere. Mars is slightly warmer because of its atmosphere. So your textbook tells you how to calculate a no greenhouse temperature. Right? And then we can measure the actual surface temperature and see what the effect of the atmosphere being there is. So atmospheres vary with altitude, and we can discuss that briefly. And we want to talk about what happens when light is incident on a molecule in the atmosphere. All right, so we're talking about some molecule of some compound, water or oxygen or CFCs, whatever it happens to be. There's different effects, and the effects vary with energy. So the lowest energy stuff can just be absorbed. The molecule stores energy. The more energetic stuff, which more energetic here means bluer, toward visible light and ultraviolet light. So the more energetic light can scatter off of particles, and it can change the photon's direction, and it can change the particle's direction of motion. Even more energetic, generally ultraviolet light, can cause the breakdown of the molecule into, separate parts, ions. And then even more energetic stuff, X-rays and gamma rays, can break the molecule down into atoms and break electrons off of the atoms. So what that tends to show us is infrared light gets absorbed, visible light is scattered, blue light more than red, X-rays and UV light can break apart molecules. Right, so at the very bottom of an atmosphere is what's called the troposphere. Temperature drops with altitude, and it tends to be warmed by the surface, by infrared light, and by convection in the atmosphere. Then above that, in the Earth's atmosphere, is what's called the stratosphere. And the temperature fluctuates. It goes up for a bit, and it goes back down for a bit. And in this layer, it's being warmed by ultraviolet light. Something in the stratosphere is absorbing ultraviolet light and storing it as heat. Then above that in an atmosphere is what's called the thermosphere. It's about 100 kilometers up. Temperature rises. What's going on here is that the atmosphere is thinning out. It's easier for the particles to move fast and to have a high kinetic energy, a high temperature. And generally, X-rays and ultraviolet light warm this layer. It ionizes gases and warms, the heat stored from breaking apart molecules. And then finally, the very top layer, the bit that fades out into space, is called the exosphere. Temperature is rising here to the point where atoms can escape into space. Not all atoms, but the fastest moving atoms can escape. and again warmed by X-rays and UV light. So I often ask students, why is the sky blue? And it's based on scattering. And I don't have a good way of showing this to you in the lab. Scattering depends on the size of the particles and the wavelength of the light. But in general, the atmosphere scatters blue light effectively and red light passes through. So when it's noon, red light can go straight to the ground, and you're basically looking at the sun when you're trying to see the red light. The blue all around it is light that's been scattered from away from you toward you. So when it's sunset or sunrise, there's a lot of atmosphere to go through, and the blue light is scattered generally away from you, whereas the red light can pass through, and so you see the red sky. So when we look at the other planets, we notice at least one interesting thing is that the Earth has this weird little, let's see if I can bring it up. Laser pointer. Right here, it has this little bump in what's effectively the stratosphere. The other planets don't have that. They have, from the surface, a cooling basically until they get to the thermosphere and then a heating up again. Earth has this little bump. That's because UV light is absorbed there by ozone molecules in the atmosphere. The stratosphere in Earth, which isn't present in the other planets, has ozone. So there's a constant stream of particles coming from the sun, the solar wind. Those particles can interact with the atmosphere, and in general, it interacts with the magnetic field of the Earth or of the planet. And you generally see it as aurora, as charged particles giving off light as they interact with the atmosphere. And it looks like that. They're real pretty. All right, so wind and weather. So we want to be clear, weather is the stuff that happens day to day, hour to hour. It's hard to predict because it can be complex, and it's the effects of temperature and pressure and wind speed and clouds. And so climate is a long-term average of the weather. Is it generally wet? Is it generally hot or cold? All right, and it's a much more predictable thing because it's taking an average of weather. It's climates are generally predictable because the weather can only, you're not going to expect it to snow in a very hot place. You can expect it to be dry or wet. You can expect it to be hot or cold. And so climate, because it's over a long term, it's more easily predictable. So on Earth, there are weather patterns over our area. Winds move west to east, and then above and below us, it moves east to west. And so here's what's going on. At the surface, you generally have cold air falling and hot air rising, and it's going to cause high pressure over the Arctic and low pressure over the equator. And so you'll have, at the ground, winds moving north to south in the northern hemisphere, and then the air rises at the equator where it's hot, and then moves south to north above that, and then falls at the poles where it's cold. And so you have a circulation cell, you have convection. So without any rotation of the Earth, you just have basically two big caps over the poles that are convection cells moving air. And so you expect the air to move north and south. But the Earth is rotating. And so things that are trying to move on a rotating object, north and south, feel forces to the east and west, what's called the Coriolis effect. Imagine you're on a merry-go-round and you try to roll an object across it. You're going to see it veer off. It's rolling in a straight line, but the merry-go-round's turning under it. I'll try to get a video of that sometime of what that kind of looks like. But that happens on the Earth too. If a chunk of air tries to move, it feels a force that causes it to drift in one direction or another. And so you get low or high pressure areas or circulation areas. You see that in storms and hurricanes. They swirl. And they swirl in different directions based on what hemisphere you're in. If you've ever heard the story of sink drains or toilets, bathtubs draining, and they drain one direction in one hemisphere and one direction in the other, that's kind of bogus. That is more an effect of how the thing's constructed. There's even a famous experiment, sort of famous experiment. Someone bought a sink in one hemisphere, watched which way it drained, and then took it to another hemisphere and it drained the same way. Is that these effects tend to be like the tiniest effect I can think of is battleships shooting shells have to account for the curvature of the Earth and the Coriolis effect when they're shooting over 20 miles or so. These are massive sized effects. You have to be the size of a hurricane to notice on a big scale these Coriolis effects. But what it does in terms of the circulation is it splits up that one circulation cell we'd expect into three. And so in these cells, you tend to have east and west motions. The wind is trying to go north-south and being bent to the east and west. Water cycle. Okay, so what can change a climate? Well, the sun is brightening very slightly over time, so there will be more energy available to be absorbed. So that will generally heat all of the planets up. Right? That's a completely true statement. It is usually not the way people talk about it. It's more of a very gradual, very slow, over millions of years process. Axis tilt absolutely changes seasons. The Earth's axis is relatively stable. We talked about precession, so climate can change over thousands of years. We'll talk about Mars in a moment. It is not nearly as stable, and it changes over a much shorter time. Right. And in general, the Earth's axis varies between 22 and 25 degrees. Not a big change. You can change the reflectivity of a planet. Right? Earth and Venus are fairly similar, except Venus is very, very reflective because it has lots of clouds comparatively. Generally, high reflectivity cools a planet, low reflectivity warms a planet. And then you can change the content of the atmosphere. The more greenhouse gas you put in an atmosphere, the warmer the atmosphere is going to end up. So how do you change the gases? Well, you can have volcanoes, you can have outgassing, evaporation, you can have impacts. Right? Volcanoes will give off gas. Liquids on the surface will evaporate or sublime. You can have particles impacting and knocking dust and gas into the atmosphere. But you can also lose gases. There's a gas at the top of the atmosphere can have enough velocity to escape. You can have particles knocked away by the solar wind. You can condense onto the surface. You can have chemical reactions with the surface. You can just lose a big chunk of it from an impact. So the content of an atmosphere can change over a long period of time. And I wanted to talk about escape for a bit. So what I'm showing you in this graph is a frequency diagram. It's counting the number of atoms that have a particular speed. And the peak here is talking about the average velocity of a particle in a gas. So if you've taken chemistry, you may have talked about that a bit. You'll certainly talk about it in physics a bit. But it's about, what's the kinetic energy of a gas? It's measuring the kinetic energy of a particle and multiplying by the number of particles. So most atoms in a gas can't escape. And what I mean is it can't reach a velocity that is greater than the escape velocity. But there's a tail here that can. And if those particles are near the top of the atmosphere, they can escape. Note that it depends on the temperature and it depends on the mass. So very light particles like hydrogen are easier to escape. Very warm particles are easier to escape. So now this is where we talk about the various planets and do they have atmospheres. And we start with the Moon and Mercury, which seem like they shouldn't. But remember the definition for an atmosphere, it's any layer of gas surrounding a planet. Is there any gas surrounding a planet? Well, yeah. The Moon and Mercury both seem to have stuff. It's extremely thin atmospheres, and the cause is from impacts. Is that the solar wind and micrometeorites impact on the surface, and they knock particles out which escape. And so you effectively have little bits of the crust as your atmosphere. So it's going to be dominated by metals, things like sodium and potassium and silicon and oxygen. And there's some evidence that there's other things like water vapor because there's ice in areas that never warm up basically in craters that are in shade. So we think the Moon and Mercury might have some ice, and so there's some evidence of, you could have some water vapor in principle, but in general, there's not much. A very, very tenuous atmosphere. There's not much we can say about it. So what's Mars like? Well, Mars has seasons and they're extreme. One is the seasons on Mars actually are affected by distance from the sun. Mars tends to have a more eccentric orbit. And so the southern hemisphere tends to experience lots of energy and then low energy, very little energy at times. And so what we see is that the ice caps on Mars, particularly the southern ice cap, is mostly water ice in the summer, and then in the winter, carbon dioxide sublimates and builds it up, and then it condenses in the summer and leaves the water. And so we see seasonal winds. So you see dust storms, which can basically obscure the surface. Axis tilt is important. Axis tilt, we think, ranges from 0 to 60 degrees, and so you get massive climate changes. And we kind of see that. We see in the polar regions where there's more permanent ice, you see layers of ice and dust where the climate has varied over time. So Mars has changed. Why? We haven't seen widespread water in about 3 billion years. And probably before that, there was an atmosphere that could have kept the surface warm. So somehow Mars has lost a bunch of atmosphere. When we look at Mars's atmosphere, it's very low pressure, very low density, mostly carbon dioxide and nitrogen, which should be very good greenhouse gases, but there's not much of it. And what we think happened is Mars is a small body, cooled off, and that lowered the amount of magnetic field, which allowed the atmosphere to be stripped off by the solar wind. It wasn't protected. So, Venus. Very thick atmosphere, very hot atmosphere, very high pressure, and the rotation of the planet is very slow. So you get very little circulation. This Coriolis effect is weak. You don't get that much weather. You get clouds that are basically stationary and not much going on. It's a very still atmosphere in a sense. And this carbon dioxide is a very strong, a very potent greenhouse gas here. So you get a very uniform oven of heat. There's not as much carbon on Earth. It's in the rocks and in the ocean. It's not in the atmosphere. So how did Venus get so hot? We're not certain. We have an idea. We think it's pretty ideal. We have to explain some stuff about the atmosphere. Basically, some of the atmosphere is unusual. The atmosphere has sulfuric acid in it, which means that there's some mineral, there's some interaction between the crust and the atmosphere. And there's some places with fast winds, which we don't understand. But in general, what we think happened is Venus had a little bit more energy. It's a little closer to the sun, and so Venus was a little warmer than the Earth. The Earth had liquid water. We think Venus had liquid water at some point. But it's a little warmer. And a little warmer means there's a little more water vapor in the atmosphere. And water vapor is a major greenhouse gas. It is very good at absorbing the infrared light. And so it absorbs light. And there's more light to absorb. So it's a little hotter, which creates more water vapor. And it gets hotter, more water vapor, more temperature. The greenhouse effect runs away. So eventually all of the water is in the atmosphere on Venus. And the heat is causing the rocks to decompose. It gives off CO2, which makes it hotter. And so eventually the temperature is high enough that hydrogen can escape if it breaks off of the oxygen. And there's more energy, so there's more UV light present from the sunlight, and the water vapor slowly breaks down and the hydrogen escapes, and the oxygen reacts with the rocks and forms carbon dioxide, and it just builds up more and more and more of Venus's current atmosphere in a runaway effect. Earth didn't do that. Earth was a little bit cooler. The water stayed liquid. And we should talk about the original atmosphere of Earth. I got distracted here for a moment. I had to pause the video. Where was I? So Earth is unique, and we want to explain why the Earth is unique. Come on, computer. There we go. In general, the Earth just didn't get as much energy from the sun as Venus did. So it's a little cooler, and the water that was present could stay liquid. And oceans are really good at absorbing carbon dioxide, so it absorbed the carbon dioxide out of the atmosphere, which allowed it to stay cooler. And it gets trapped in carbon in the rocks as carbonates. So Earth's original atmosphere is going to be nitrogen and water vapor, and some heavier stuff, like argon and a little bit of carbon dioxide. But the oxygen has to come from somewhere, and it comes from the very early life that formed on Earth. Plants, uh, you know, plankton, the little microscopic uh, cells are going to give off oxygen, breaking down carbon dioxide. So, with oxygen available, ultraviolet light breaks up some oxygen and it forms ozone. And that ozone is good at absorbing UV light. So, without the plants, without the without the without the oxygen producing life on Earth, there wouldn't be a stratosphere which absorbs UV light. So Earth's climate is fairly stable in the sense that there is a feedback cycle that can, if it gets too cold, it warms it up. If it gets too warm, it cools it down a bit. Which I want to warn you, this is not a perfect story. You've heard of the water cycle. We're going to talk about the carbon dioxide cycle. Is what can the Earth do to moderate the temperature? So atmospheric carbon dioxide will dissolve in rainwater, which carries minerals into the ocean, and that's going to form carbonate rock on the ocean floor. So the ocean floor is a store of carbon dioxide. Now, the ocean floor is also recycled, and so in volcanoes, you'll get outgassing of carbon dioxide, and carbon dioxide cycles through the atmosphere over time. So as that happens, if the temperature changes, different parts of this process will be affected. And so what happens is cooling means that you have less weather. You have less water to take the carbon dioxide out of the atmosphere, and the volcanoes will emit more carbon dioxide, which will strengthen the greenhouse effect and warms up the Earth. So if you have more heating, then you'll have more weather, and rain will pull CO2 out of the atmosphere back into the oceans, and it'll cool down, it'll weaken the greenhouse effect. And so this seems very nice. Seems like we have a thermostat effect. It holds the Earth's temperature at a relatively fixed level. You do get cycles, right? You get long-term changes in what we call ice ages, where the temperature drops, and so Earth freezes over in a sense, or mostly freezes over, and you have lots of volcanoes to add CO2 to the Earth heats up again. And so you'll have warm periods where there's lots of weather to pull CO2 out of the atmosphere. And it goes through these ice age cycles. So this is the thing is, we'll show you the periodic effect over time of the CO2 cycle. It assumes that the total amount of carbon dioxide is roughly stationary. It doesn't say anything about what happens if a bunch of life suddenly creates more carbon dioxide. And that's what humans are effectively doing. So humans mess up atmospheres The first thing we got caught doing was we like our hairspray. We put chemicals, chlorofluorocarbons, which easily got out into the atmosphere, and they're generally very inert, but they interact with ozone and they cause holes in the ozone layer in the stratosphere where UV light can get through, or more UV light can get through. Right, and then humans also, in the general quest to build more stuff, we endanger species. But the big thing is that humans can take stores of carbon dioxide and use it as fuel. And so that produces more carbon dioxide in the atmosphere. And there's been a general warming trend ever since effectively the industrial period of humanity has formed more and more carbon dioxide in the atmosphere, which is correlated with an increase in temperature. So here's the thing: we can measure uh, the temperature cycle and the carbon dioxide cycle over a long period of time, over thousands of years. And it's cyclical. There's ice ages. It warms and cools in a cycle as we expect. The carbon dioxide cycle works up until about 1750. And then it's not cycling as we'd expect. And so we can see seasonal changes. And we can see that it just keeps going up and up and up. And most of that change is over basically the last 50 or so years. It's not that much change. So our understanding of things, right? The CO2 cycle depends on a relatively steady amount of carbon dioxide. We don't know what happens if you continue to increase. What happens if the CO2 is in the atmosphere and the oceans have absorbed all of it that they can? Right? We don't know what happens if we outpace the CO2 cycle. So we kind of get the gist of it, and we're kind of seeing it now. Is ocean levels are rising. The If you don't believe me, please take a vacation to Miami. It is generally underwater a lot of the time, in the sense that the sewer system doesn't work anymore because of the tides. They built it expecting one water level, and then the water has risen, and things don't work as well anymore. Storms are more intense. As I'm talking about this, we are on Hurricane Epsilon, which is unprecedented in the history of tropical storms. And storms are generally stronger than when I was a child. That's for certain. More frequent and more energetic storms. And of course, another thing humans do is use up water everywhere. So there's kind of a question as to where are we going to be able to produce food? Where is water going to show up? And, this is the thing. When I was in college, we went to Cape Hatteras and studied the groundwater there. Basically, measured the conductivity of the soil and of the lower layers with big, massive electrical arrays. And what it did was we measured effectively the salinity of the groundwater. We measured how much the water from the ocean was encroaching on the water table on the Outer Banks. And over time, what's happened is more and more salt water has gotten into the freshwater supply. There's less and less water to drink. And it's happening in places for different reasons. There's other places where we just use too much water because we want to have a city in the middle of a desert, for example. And ultimately, there's going to be areas where the water is going to rise, the temperature is going to heat up. People aren't going to want to live there. They're going to want to live somewhere else. And when you have groups of people coming together, you're going to have unrest. So we're kind of seeing some of that. It's the problem with life is we're living in history. And we're always living in interesting times. So go outside and enjoy the day today. It is a beautiful day, and it might be the last beautiful day this fall. Who knows? Go enjoy it.